In December 2025, Anthropic donated the Model Context Protocol to the Linux Foundation, establishing it as the founding project of the Agentic AI Foundation. This governance shift established MCP as a vendor-neutral standard for highly concurrent enterprise infrastructure. On July 28, 2026, the project lead maintainers published a release candidate that rewrites the protocol's foundation. The first major pillar of this rewrite is the complete removal of protocol-level sessions. The second is a strict RFC-compliant standardization of authorization. These changes respond to a specific technical reality. Traditional REST and gRPC security models do not account for the recursive nature of LLM agentic loops. As deployments move toward the July deadline, teams are evaluating 5 trust boundaries that fall outside standard network defense. This diagram illustrates the core MCP triad. The host application, client library, and servers each hold highly sensitive keys. The host controls LLM API keys and OAuth tokens. The client manages routing state, while the server secures back-end database credentials. Because of this distribution of credentials, you must treat every single server, even the ones your own engineers wrote, as an untrusted third-party vendor. This architecture introduces 5 distinct trust boundaries, where data and intent cross between these entities. The most dangerous blind spot for enterprise teams lies at the 5th boundary, the connection from the tool output back to the LLM. Traditional scanners treat tool output as inert data, but in an MCP workflow, the LLM reads that output directly as an executable instruction. The echo leak vulnerability demonstrates how this boundary fails. Looking at this flow, the user asks to summarize a benign invoice document, but embedded within is an injected instruction. The LLM reads it, overrides the prompt, and autonomously reads the host's password file. The exploit packages that stolen data into a markdown image URL. When the client renders the image, the data is silently exfiltrated to the attacker. When you remove human confirmation from autonomous agentic loops, prompt injection graduates from a chat anomaly to immediate, automated lateral movement. That lateral movement thrives on 2 specific attack vectors targeting the client-server boundary: tool poisoning and rug pulls. This vulnerability table highlights CVE 2025-54136, a classic rug pull. A malicious server changes a tool's description or schema to include destructive commands long after the user grants initial approval, hijacking the model's behavior. To neutralize this, engineering teams must implement strict client-side hash pinning. By hashing the tool's name, description, and schema at first approval, any subsequent authentication triggers an immediate halt and requires reauthorization. Beyond tool tampering, the stateful 2025 architecture suffered from severe authorization failures, primarily the confused deputy problem. If a server's service account fails per call identity checks, users can trick it into fetching unauthorized data. This compounds with token pass-through. An attacker could steal a token intended for one service and successfully replay it against another. Combining poor token binding with vulnerable tool boundaries enables a specific attack pattern: cross-server parasitic chains. A compromised server returns an instruction forcing the LLM to execute a destructive tool on an unrelated, highly privileged server. Because the LLM uses the active session, the second server trusts the request implicitly. The 2025 architecture allowed implicit trust to cascade disastrously across the network. Fixing this required the Agentic AI Foundation to completely redesign the protocol. The July 2026 specification resolves these structural fragilities by removing sessions from the core protocol. Previously, remote servers required sticky routing and deep packet inspection simply to maintain the protocol's MCP session ID header. This created a severe operational bottleneck. The 2026 update permanently removes both the initialization handshake and the session ID header from the network layer. Traffic is now routed statelessly, dictated entirely by the MCP method and MCP name headers attached to each request. Session state has not disappeared, it is now handled explicitly. Servers mint specific handles, like a basket ID, and the LLM passes that handle back as an ordinary argument during subsequent calls. This forces the model to logically reason about the handles, compose them across tools, and hand them off between steps, rather than relying on hidden network state it cannot verify. For operations teams, this completely removes the engineering burden of maintaining shared session stores at the enterprise gateway level. Migrating state from the protocol to the application layer allows infrastructure to scale behind round-robin load balancers while neutralizing session pinning attacks. The final defensive pillar of the 2026 update transforms MCP servers into formal OAuth 2.1 resource servers. The specification now strictly mandates the implementation of RFC 8707, standardizing the use of resource indicators. Resource indicators force clients to explicitly bind their token requests to specific MCP server audiences. This single requirement mathematically neutralizes the token pass-through and confused deputy attacks. A token minted for server A cannot physically be executed on server B. Furthermore, the specification deprecates dynamic client registration in favor of cryptographic client ID metadata documents, deliberately engineering mix-up attacks out of the system. Combining this new stateless routing architecture with strict OAuth validation creates an uncompromising, highly resilient enterprise gateway for your network. For engineering teams, the mandate before July 28th is clear. First, you must strip all session dependencies from your deployment and validate your architecture behind standard round-robin load balancers. Second, you must implement RFC 9728 discovery endpoints to support the new OAuth-protected resource routing. The Linux Foundation has engineered a secure zero-trust protocol, but the ultimate responsibility of enforcing the fifth trust boundary and keeping your agentic loops contained rests entirely on your team's execution.